that describe relative motion analysis using rotating axis. Let me clear a few things on here. Right now, since this rotating frame has not aligned with O, that's why I have to add this term here, because your rotating axis can translate with certain velocity or acceleration. That's why I have to include that. However, if your rotating frame is aligned with O, then your first term will just 0, okay? So in many cases, your rotating axis is aligned with the fixed frame, so we don't include a first term. And then another things that I want to make clear is that in a fixed frame, our unit vector is capital I and capital J, and the K, capital K, that out of your screen, and the unit vector of your local frame is small I and small j, okay? And then the origin is A, and the object has a C point. In that case, this equation is valid under this with this picture. I'm not sure whether this can be set in the amusement park or not, but let's say this is a big rod and the person just sit on the rod, and then this big rod is rotating with a certain angular velocity. If you look at this equation, right now all the red color represents your position vector and velocity or acceleration term expressed with respect to rotating frame. So what I mean by is rotating frame is you set the rotating frame x, y, and then however we have a fixed frame, so our fixed frame is on the ground, okay? So we have a fixed frame on the ground, and this rotating frame is rotating. Then if you just describe the persons with respect to rotating frame, the person sits, does not move, right? That's why your velocity and acceleration should be all 0, because these are all the velocity and acceleration expressed relative to rotating frame. But the person sits and stand still, so the velocity acceleration will be 0. And then we assume that this rod is rotating with the constant angular velocity. That means your omega dot will be 0. Then the acceleration equations get simplified like that. So this is omega square cross product, omega cross product r vector. So this is minus omega square and r vector like that. So what does that mean? So if you observed the person's motion from your fixed frame, I call that is inertia frame. Then certainly there's acceleration, because acceleration is negative omega square r. So what is that acceleration? Actually, because the body is rotating, okay? So as long as certain motion, certain object is rotating, even though the motion is rotated at a constant angular velocity, your body is accelerating. Why? Because the direction is always keep changing. So because we have the acceleration, there must be the force, because F is equal to ma. So if you multiply the mass, the acceleration, it must be force. So what's the direction of this acceleration? So inward, right? So if you just imagine that this is a person just sitting like that, then some acceleration is directed to the center, which is omega squared over r. So this is the accelerations. That's why this accelerations is caused by the friction force actually. So if someone just sit on the rod, so this is rod, and the person just sit on the rod, so basically the friction force from the rod, this is friction force, caused this acceleration. So that's why the direction of the velocities keep changing when you observe the persons from the inertia frame. Imagine that you observed the person with respect to a rotating frame. Okay? From rotating axis, so I would say this is non-inertia frame. So as long as you sit on the rod and just observe the person just sit there. So body is still not moving, right? That means there must be force that counterbalance your friction. Okay? Because this is a person like that, but we certainly says there's a friction force that caused this acceleration. But when you observe this person with respect to the rotating frame, the person is not accelerating. The person is not accelerated, which means there might be some force that counterbalance this friction force. We have to come up with that force. That is centrifugal force. Okay, but this centrifugal force is fictitious force because we came up with this force to describe this phenomena. Otherwise, there might be acceleration due to this friction, but when you observe the person in the rotating frame, the person sits still, then this force must be counterbalanced with the centrifugal force. That's why the centrifugal force is only the force you can feel in the rotating frame. If you observe the person from the outside of rotating frame, then there's no centrifugal force actually. Okay, so that's why we call this is fictitious force. This is not actual force, but we have to come up with a certain force to describe the motion with respect to your rotating axis, which is non-inertia frame. Right now they just throw and catch the ball. In a rotating frame, they just throw the ball. Okay, so when you observe the ball motion from the outside of rotating axis, the ball is just moved to the straight line. Look at that. The ball is just moved to the straight line. Right? That makes sense. But if you observe the ball inside the rotating frame, when someone just throws the ball is deviated. The ball changed its direction. What happened? It looks like some force is acting on the ball. That's why it caused the ball change its direction. Right? It's very strange. Observe the throw in the rotating frame. Yes, there's some force kind of pushing to the left. So we have to come up with that kind of force. That is fictitious force. Actually, there's no force. However, in order to express or explain those kind of change in the direction, we have to come up with some force which is fictitious force. And centrifugal force is one of those fictitious force. So let's just look at this another example here. Let's say the disk is rotating. On the center, there's one device that launches a ball to the straight line. Okay, this is my just X, and then certain rotating frame is fixed on your disk, and this is rotating with a certain angular velocity. So since this, even though this is rotating, when after this launch the ball just move to the straight line, right? So when you observe the ball from your inertia frame, okay, then there's no acceleration, right? No acceleration. That means this left term should be 0, okay? And then we assume there's no acceleration, angular acceleration. This one is 0. And then right now, that's why if I just write down these equations, this is minus omega square r CA, and then 2 omega cross product the V A, and then certain acceleration with respect to the rotating frame. This may not be 0 right now, okay? And then how about when you observe the ball from the non-inertia frame? Okay. As I showed you in the small video clip, if you observe this ball with inside the rotating frame, the ball changes its direction, right? So how do we explain the force or accelerations that cause the ball to change its direction? So from this equation, so right now from this equation ACA, this is an acceleration with respect to your rotating frame A, is this term minus cross product this one, right? So if you look at this one, so we have a certain acceleration, that direction. So let's say this is your disk, okay, and then the ball is launched, and the ball is changed the direction like that. So what's the direction of this acceleration? So direction of acceleration here is, this is opposite to this is actually centrifugal. This is the term that I explained for centrifugal force, centrifugal acceleration. So this is actually this is center, so this is actually the out of your center, so this is omega square r term. And then this is omega cross product velocity V. That direction is this way, okay? This is 2 omega and V. So that's why the acceleration is, the total acceleration is this one. This is ACA. So that's why the ball is kind of change its direction to this direction. However, when you observe this object C from the outside of the rotating axis, there's no acceleration at all. But if you observe this one inside the rotating frame, it changed the direction. That's why it must have certain accelerations. That acceleration can be expressed or explained by these two terms. So this term, okay, so that's why velocity cross product V, this Coriolis term, explain components of acceleration in motion only observed from a non-inertia frame. So what is non-inertia frame? Non-inertia frame is a frame of reference that is undergoing acceleration with respect to an inertia frame. So those rotating frame is non-inertia because it's rotating, it's accelerated actually. So that's why in order to explain the phenomena observed from your rotating axis, this Coriolis term actually explains that kind of deviation of the motions in this case.